Wiring an autonomous language model directly to a production database is an unacceptable operational risk that can expose your entire enterprise to catastrophic failure. A raw text-to-SQL pipeline fails predictably under enterprise conditions. Language models hallucinate table names. They execute unconstrained, massive table joins that drag down performance. Most critically, an open interface provides a direct vector for SQL injection attacks. Consider a mid-market SaaS analytics database containing 3 million rows of subscription metrics, usage logs, and revenue events, spread across multiple tables. Extracting accurate insights from this volume of data requires precise execution. To safely extract that intelligence, the system must completely isolate the reasoning engine from the actual execution environment. This flowchart maps a decoupled data analyst agent. It begins at the top. A user CLI request passes to the data analyst agent. Below, the MCP bridge translates actions into standard formats for the FastMCP server, the strict intermediary. By forcing all interaction through the model context protocol, the architecture ensures every request is standardized and validated before a single query is formulated. At the top of this internal trace, the Azure OpenAI function calling loop uses a multi-turn reasoning trace. It cannot touch data directly. Instead, the MCP bridge translates its intent into standard MCP definitions, mapping strictly to tools exposed by the FastMCP server, like list tables. This forces the language model to act methodically. It has to retrieve the schema, understand the column definitions, and formulate a step-by-step execution plan based entirely on predefined parameters. Confining the LLM to validated schemas ensures it reasons logically, neutralizing any attempt to fire rogue ad hoc commands from the edge of the network. We can see this logic applied to a complex enterprise problem, analyzing a trend in monthly recurring revenue and isolating a spike in customer churn. Asked about the MRR trend, the agent inspects tables and executes a safe template query. Investigating an August customer drop, it triggers a curiosity loop via cohort analysis. It successfully isolates the root cause, enterprise non-renewals, and proactively proposes an actionable A/B test. This markdown document is what the end user actually receives. The messy, multi-step backend work is synthesized into a clear, formatted business insight. The ability to chain sequential functions based on intermediate data results elevates a simple chat interface into a capable, autonomous analyst. This design rationale table highlights the necessity of hybrid queries. Relying exclusively on fast, safe templates restricts the system's analytical depth. Ad hoc queries are required for flexibility, but they carry significant risk. Returning to the execution trace, every ad hoc query must survive a multi-layered safety gauntlet. The system enforces parameterization and AST validation, blocking any attempt to alter data. Queries face strict timeouts and row limits before entering the read-only database connection pool. This defense-in-depth architecture gives the LLM the intellectual freedom to write dynamic queries, while guaranteeing it cannot degrade or alter the underlying database. Extracting data safely is only the first half of the process. The results must then be presented in a format useful to the business. Different stakeholders operate on different visualization platforms. To account for this, the system implements triple dashboard adapters. Looking at the right side of the architecture diagram, safe query results flow back up to the FastMCP server, where they are routed into the dashboard tools node. The agent can package the analysis as a portable JSON configuration to plug directly into Grafana, or it can render dynamic Plotly HTML components for immediate browser viewing. Utilizing MCP to standardizing these output configurations creates a truly vendor-agnostic tool, allowing the agent's insights to integrate directly into an enterprise's existing reporting pipelines. An AI agent's utility in an enterprise setting scales directly with its governance and auditability. At the infrastructure level, the system enforces hard rate limits, capping requests at 100 queries per hour to prevent compute abuse. Furthermore, an evaluation framework-first approach mandates that query correctness and efficiency metrics are continually measured. All of this complex routing, validation, and governance is entirely abstracted away from the end user. This CLI table outlines the final user interface. Stakeholders interact via simple / commands or simply ask natural language questions.
Commands like /history retrieve the conversational context, allowing the user to seamlessly ask follow-up questions while safety layers execute silently. The prompt is translated, intent is mapped to standardized tools, and resulting queries pass through rigorous validation gates before returning as structured data. By isolating the language model reasoning behind precise MCP tool definitions and a rigid syntax validator, the architecture proves that deep analytical autonomy and absolute data security can operate together in production.